Welcome back to the channel, guys. Welcome back to atomic and molecular quick revision. So from the last few videos we are talking about the quick revision of atomic and molecular physics. In the last video we discussed couple of things. In this video we are going to talk about vector atom model, and this is the third part. The previous part you can see by going to the videos list on our YouTube channel Physics Hub. So let's start vector atom model. So the total angular momentum of any atom results from the combination of orbital L and the spin S angular momentum of its electrons, and angular momentum is a vector quantity. That is why we can represent this angular momentum by means of a vector, and it is obtained by the addition of orbital and spin angular momentum, and that is why it is called vector atom model of the atom. You are adding orbital and spin angular momentum vectorally, and the model based on that is known as the vector atom model. Now let us consider some atom whose number of electron in the outermost shell is 1. Okay, so there are some atoms like hydrogen or lithium or sodium. So what they have some closed shell, and additionally they have one electron at the outermost shell. So it is something like that. I'm not drawing, I'm just drawing in a very rough manner. So for these all are called one electron atom. Okay, one electron atom in the sense one electron at their outermost shell and the remaining is closed shell. So the last one electron is basically determining the orbital and spin angular momentum of the atom, because the remaining electrons which are forming the closed shell, they vanish in pairs. Okay, whether it is orbital or spin. So what this last single electron, if L is the orbital angular momentum, S is the spin quantum angular momentum, then we can write the sum of them by a total quantum angular momentum J is equals to L plus S. Okay, so this is the relation you already know. Now we can also write in terms of the quantum number. If you write J is the total quantum number, okay, L is the orbital quantum number, S is the spin quantum number. These are quantum numbers. So what about this J? It will behave the same way L and S behaves. So J will be root over J into J plus 1, and the unit is h cut, and J is equals to L plus minus S. It is equals to L plus minus half. You will consider S. If L and S are parallel, it will consider minus S. L and S are anti-parallel. In this way these two things work. Now what is the value of J corresponding to the J direction? What I am talking about is, let's say we have something like this. This is your Z cap direction, okay, and this is your J. So what will be the component of J along this direction, Z cap direction? That will be given by Jz, and the value of Jz is find out to be Mj h cut, where the values of Mj will lie between minus J to plus J. So the value Mj can take are minus J plus 1, minus J plus 2, and so on. It will go up to 0, then 1, 2, 3 up to J. So how many total values it can get? It can get around 2J, total 2J plus 1, this one value for this 0 value. So total 2J plus 1 values it can take. Now in one electron atom there are only two possible orientations. Electron may be either up or it may be either down. Okay, we'll talk about this later on. For the time being, you see, in an one electron atom, if you talk about an one electron atom, in one electron atom, if you talk about, there are only two orientations, two relative orientations possible, corresponding to, look, the first combination will be J is equals to L plus S, and because of that, so that your J value, modulus of J value must be greater than modulus of L value. Let us try to understand with an image. J is equals to L plus S. So let's talk about this. This is L, this is S. Okay, and they are added vectorally, and you get this. You see, this is your L, this is your S. So L plus S they have added vectorally and give rise to this J, and as you can see, modulus of J will be more than modulus of L. Simple. This is the first case. Second possibility may be J is equals to L minus S. So if J is equals to L minus S, then in that case your J will be less than L. Let's try to understand it pictorially again. So let's say this is your L, okay, and this is your S, this is your J. So in this way you can realize the scenario. This is your L and minus S, so it is going in this direction. So this will be your J, and obviously you can see J is less than L. So in this way, two relative orientations are possible. Okay. Okay. Now let's get back to this. The angular momenta of the atomic electrons S and L interact magnetically. S and L interact magnetically, which is known as the spin orbit coupling. The coupling between L and S, that is called spin orbit coupling or LS coupling. They exert torque on each other. These internal torques do not change the magnitude of vector L and S, but they cause them to precise. Look, laser point O पे है ना. Okay. They cause them to precess uniformly about the resultant. What is the resultant of J and S? Sorry, L and S. The resultant is J. So this internal torque created from the coupling of LS spin orbit coupling cause them to precess about their resultant J. Right? If the atom is in free space, there is no external torque acting on them, so total angular momentum J will remain conserved in magnitude and direction. So that is why you get a fixed J value, constant, conserved in magnitude and direction. So the angle between L and S will remain invariant. Whatever be the angle L and S, that will remain invariant for this case. Understood? I hope you understand. Now look at this scenario. Here what has been done? This is not in free space now. An additional external magnetic field has been applied. So what will happen? J, L and S is precessing about J, and the resultant will additionally start precessing about the direction of the applied magnetic field B. Okay, so let's talk about this. Since we know this total angular momentum J is given by sum of L and S, then what we can write? We can write J dot J is equals to L plus S dot L plus S. Simple as that. So modulus of Z square is equals to modulus of L square plus modulus of L square plus modulus of S square plus 2 times modulus of L into modulus of S into angle between L and S, cos theta. So from this cos, let's write it cos of angle between L and S in this way. Look, when there is no magnetic field, the angle between L and S was conserved or fixed, but what will happen when there is an external magnetic field? Then the formula between the cos cos of the angle between L and S becomes J square minus L square minus S square divided by 2 times L dot S, L into S. Now if you write in terms of the quantum number, we can write it J into J plus 1 into H cut square, L into L plus 1 into H cut square minus S into S plus 1 into H cut square taken common, and in the denominator also you get L into L plus 1 H cut and S into S plus 1 H cut. So H cut square coming cancelling from both numerator and denominator, and as you get this result. This is overall the vector atom model of one electron. This can also be extended to many electron atoms. So this is precisely the vector atom model for one electron atom. So what we have done, let me summarize this. So we have considered this vector atom model for one electron atom, whose the atoms where only one electron is situated at the outermost shell. Okay, the previous shell are closed shell, so the last one electron is deciding the orbital spin, angular momentum of the whole atom. Now let's try some problem. Okay, so the problem is like this. Let me just write the problem for you. Calculate the possible orientations of the total angular momentum vector J. Okay, total angular momentum vector J corresponding to J is equals to 3 by 2 with respect to the magnetic field along the Z axis. So as I told you earlier also, that whenever there is no magnetic field, the J was remaining conserved in magnitude and direction. Now as there is some applied magnetic field, then it will not remain conserved. Okay, so let's consider this is your Z cap direction. This is your Z cap direction. So one value we have J, that is 3 by 2, and you know the total angular momentum J value is root over J into J plus 1 H cut, and JZ is equals to MJ H cut. These two things we know. So for J is equals to 3 by 2, what will be the values of MJ? MJ will be 3 by 2, half, minus half, and minus 3 by 2. So angle cos theta, if you consider it like this, this is J and this is Z direction. So this is basically what JZ is. So what will be the JZ value? Cos of this J. So cos theta, from this figure we can write it is like JZ upon J. This is the component JZ and this is the total J. So JZ is equals to MJ H cut and J is equals to this. So this is equals to MJ divided by root over J into J plus 1. So as you can see, J value is fixed, but MJ, how many values of MJ are there? 4 values of MJ are there. So how many cos theta values you will get? You will get 4 cos theta values corresponding to 3 by 2, corresponding to half, corresponding to minus half, corresponding to minus 3 by 2. So we will get 4 values. 4 values means 4 angle of theta, means 4 possible directions, 4 possible MJ values you will get. One is this 3 by 2. Okay, let's try to draw it in this way. plus 3 by 2 plus half minus half and minus 3 by 2. In this way you can draw it. Excuse me for my drawing, but you can understand it in this way. So this value corresponding to mj equals to plus 3 by 2, this is corresponding to mj equals to half, this is corresponding to mj equals to minus half, this is corresponding to mj equals to minus 3 by 2. And what is the value of jz? You can find it along. So what will be this value? Jz equals to mj h cut. So this will be 3 by 2 h cut, this will be half h cut, this will be minus half h cut, this will be minus 3 by 2 h cut. Okay, so possible orientations you have to find out. So possible orientations you can easily get it from here by taking the different values of mj. By putting this value of mj, you get the values of cos theta. So precisely I am writing the value, you can check it, you can match it. 0.775, 0.258, minus 0.258 and minus 0.77. So in this way you can calculate. Now I am giving you one problem as homework. You can do it at home and you can let me know the answer in the comment section. In the vector atom model, the angular momentum applied to an atom, what is the minimum angle in degrees in integer made by the orbital angular momentum vector and the positive z-axis for a 2p electron. So you can consider it like the way we did it for J, same thing will go for L. Okay, so do it and you can let me know in the comment section. So before I stop this video guys, let me tell you an academic goal is going on. Stay ahead in your preparation journey. You can get 20% off plus up to 1 month free extension on CSIR-NET subscription. This offer is valid till May 31st and you can target for CSIR-NET June 2024 or December 23. You have to utilize the referral code Physics Hub for getting the maximum benefits. So this is my profile. You can search it on Unacademy and you will get all the 9 units starting from mathematical physics to nuclear particle. All the 9 units are available. You just need to take a single subscription using our referral code Physics Hub to get this all 9 units. The whole physical science syllabus you can cover by taking a single subscription using referral code Physics Hub. Lot of benefits are there. You can pause and read them all. Okay, so this is all for this video guys. Thank you very much. If you are new to this channel, please subscribe to the channel and don't forget to press the bell icon. Finally, thanks for watching.